and short period secondary microseism. One thing is very clear from this figure. Whatever be the reasons, these bands look very differently both seasonally and spatially. These bands are driven by storms and sea ice in various oceans surrounding Alaska. Hence, understanding these patterns are important because they carry valuable and quantifiable information about these phenomena. By the end of this presentation, we will again revisit to this figure, and hopefully this will make much more sense to you than it is doing now. Further, first let's understand what secondary microseisms. Secondary microseisms are produced by ocean waves. When ocean waves of similar frequency travels in opposite direction, they interfere together to form standing waves. It is this standing waves which then produces secondary microseism. This is a spectrogram for the station K13A located in Alaska. If you look at the 5 to 10 second band specifically, you can see a clear seasonal variation. This signal is stronger in winter and quieter in summer. If you take an average over this band, it will look like this. This is what I plotted as secondary microseism in the previous figure. Now we know what is secondary microseism. The next step is to identify the source region of this signal. For that, we select 154 different seismic stations spread across Alaska, and we divide Alaska into 6 different regions: Northwest, Northeast, Central West, Central East, Southwest, and Southeast. We calculate the mean secondary microseismic power from each of this region and correlate it with ocean wave heights from the surrounding ocean. This will result in 6 correlation maps corresponding to each 6 regions. We did this for a time series ranging 3-year-long time series from 2018 to 2021. I'm going to just show a single map today, which corresponds to the Northeast region. Interestingly, the secondary microseism from the Northeast region of Alaska correlates well with the wave heights from the Gulf of Alaska. Not to the waves from Bering Sea, Barefoot Sea, or Chukchi Sea, but to the Gulf of Alaska. That means the Gulf of Alaska is the dominant source of secondary microseisms in the region. This was true for all other regions we looked at. Please remember that Alaska is a big state. That means from the southern coast to northern coast, it's more than 1,000 kilometers in length. So we can also say that the secondary microseism produced in Gulf of Alaska can travel farther distances without significant attenuation. I want you to keep these 2 inferences in mind moving forward. Now, let's talk about short period secondary microseism. This is a spectrogram for station A21K located in northern Alaska. If you specifically look at the 1 to 2 second band, the signal will look like this. Unlike secondary microseism, this band is noisier in summer and quieter in winter, opposite to secondary microseism actually. Why this is happening like this? Well, if you look at the sea ice concentration within a couple of kilometers away from the station, the picture becomes more clearer. This is the sea ice concentration, and you can see there is a clear anti-correlation between these 2 signals. When the sea ice concentration is high, the short period secondary microseismic power is low. As the sea ice melts away, ocean waves starts to pick up in the ocean, and short period secondary microseismic power increases. So now we know what is short period secondary microseism and how sea ice affects it. Now let's find out the source region of this signal. We did the same cross correlation analysis, but this time with stations. And you can see, unlike secondary microseism, the short period secondary microseism are driven by ocean waves within a couple of 100 kilometers away from the station. If you look at the panel B for station H21K, you can also see that the correlation values are becoming smaller, and the area of higher correlation is becoming more diffuse as you move from coast to interior. This means that the short period secondary microseism accumulates quite faster as you move from coast to interior. Please keep these 2 inferences in mind too. So now let's revisit the figure I showed you before. Okay, this is the secondary microseismic signal from the station A21K. Clearly, the signal is noisier in winter and quieter in summer. Why? That's because the number of storms and the strength of storms in Gulf of Alaska is stronger in winter. We also know that the signal travel farther distances without significant attenuation. So we expect to see similar pattern across Alaska. And that's what we see. If you look at the station Q19K, the bottom right panel, and compare it with the A21K, top left panel, we can see the absolute value of the secondary microseismic power is higher in Q19K. That's because it's closer to the source region. Now, let's look at the short period secondary microseismic power. You can see the clear onset of sea ice in December from the signal. We also know that the signal attenuates quite rapidly as we move from coast to interior. Let's see if that's what we see. By the time we reach H21K, the short period secondary microseism power attenuates more than 40 decibels. As we even move southwards, we come close to the southern coast of Alaska. So we expect an increase in short period secondary microseismic power. And that's what we observe. Now let's compare short period secondary microseismic power with the secondary microseismic. At Q19K, the southern station, both the signal oscillate in phase because both of these signals are produced by waveheads from Gulf of Alaska. As you move north, when we reach A21K, we can see that these signals oscillate out of phase, almost exactly opposite to each other. That's because even though Gulf of Alaska produces secondary microseism, the short period secondary microseism is driven by coastal sea states. So with that, I will take questions.